Hello friends, welcome to my YouTube channel Easy Aviation. Here we discuss about the short simple topic about the aviation field. Today's topic of discussion, as you can see, is Mach number. So Mach number, a little bit of history. It is coined by Austrian professor. His name was Ernst Mach, and in 1893 he had published one book, Science of Mechanics. So in that he has told about the relation between the speed of sound and the speed or the velocity of the object, and he told about the significance of the Mach. I'll just write Ernst Mach. So this is about the history part. So I'll just explain what is Mach number. Mach number is defined by Mach m, and it is the ratio of the velocity of the object divided by the speed of sound or the velocity of the sound. Since it is the ratio of two speed to velocity, that's why this Mach number does not have any unit. Okay, so simple till now. So the velocity of the object, it is moving through a surrounding, and the speed of the sound in that surrounding is there's a denoted as V upon C. So C is the speed of sound and V is the velocity of the object. So the sound speed in the surrounding and is denoted by C, and the object which is moving with the velocity V is denoted by V, and the ratio of both of them is Mach. So if we say any aircraft is going with at 0.5 Mach, that means it is moving at half the velocity of sound in that surrounding. Okay, now till now it is simple, but things get complicated when the speed of sound, as we know, it is not constant. And I'll take another page. So speed of sound C, I'll write here speed of sound. C is also coined for the speed of light. So speed of sound C is calculated as under root of gamma RT upon M. So gamma is the specific heat constant, which is actually 1.4. R is the joules constant. I'm not sure about the value, is 283 or something. It's also a constant, K. And T is the temperature of the surrounding which I keep telling in the previous page. So T is the temperature of that surrounding, and M is the molar mass of the gas which is present in the surrounding. So when we speak about the aircraft moving in a surrounding, then this gamma R and M molar mass, they does not vary much. But if we speak about doing a prototype testing in a controlled ambient environment, at that time this molar mass is of specific significance, because the gas which is available in the environment, like how much amount of nitrogen, oxygen, argon, or the mixture of the gas which is available, and accordingly they can check the temperature, and that's how the speed of the sound is calculated. But when we talk about the open environment, when the aircraft is moving in the open surrounding, then C we can write is proportional to the under root of temperature. So as we increase the temperature, the speed of sound also increases with a factor of this under root. In one of my video, I have discussed about the change in temperature in atmosphere. So as we go up, this is sea level as per ISA condition. As we go up till 11 kilometer, like till the end of troposphere, temperature reduces at the rate of minus 6.5 degrees centigrade per kilometer. I'll take another page. So as we go up, this is sea level, and as we are going up till troposphere, the lapse rate, we call it alpha, is minus 6.5. Okay, I'll write 6.5 degrees centigrade per kilometer. So this gives an inference that if the aircraft, let's say this is sea level, if the aircraft is flying at particular height h, if it height is increased at this with capital H, the speed of sound here is more as compared to this. So I'll write it with a bigger arrow and this a smaller arrow. So the speed of sound, or I'll denote like this, C1 C2. So C1 speed of sound is greater than C2. That means the aircraft, if it is flying, if we calculate the Mach, which is the velocity of the aircraft, and the speed of sound C, so if it is flying near to the sea level, or it is not flying at a very high height, then it has to go to higher velocity to reach Mach 1, because C is more. You can write it down, work it out. Since the speed of sound, like the aircraft has to reach the velocity to the speed of sound to go to Mach 1, right? And similarly, if the aircraft is flying at a very high height at a very low speed, the Mach Mach number is equal to 1, or Mach 1 is achieved easily, or Mach 2 or the higher Mach number can be achieved easily at a very high height because the speed of sound is low. I hope I made myself clear. You can stop the video, can write it down and work it out. I'll just give an example. Like when we reach to stratosphere, the temperature is minus 60 degrees centigrade, and temperature at sea level it's 15 degrees centigrade. So when we calculate using that formula which I had just discussed, the speed of sound, that is under root of gamma RT upon molar mass. So at speed of sound at sea level is 340 meter per second, if we put all the formulas of into this. However, if we check the speed of level at troposphere, like I'll write TT, at the end of troposphere, which is at minus 60 degrees centigrade, definitely by putting that alpha or this lapse rate into this, we'll find the speed of sound is reduced to 295 degree. 295 meter per second. The speed has been reduced to this much. So this give you a clear idea that as we go up, the speed of sound increases, and it's easier to for the aircraft to reach to Mach 1 easy or the faster, on a faster rate, as if the aircraft is flying lower to the near to the ground, or to the place where the temperature is less. I'll reiterate, rather than the height, the temperature is the factor. Temperature, I'll write, temperature is the factor which decides how fast the aircraft reach or hit, I'll write here only, hit Mach 1. So at lower temperature it's easy for the aircraft to reach Mach 1. At higher temperature it's difficult, or it'll take time to reach Mach 1. If any issues, any doubt, any specific clarification is required in this regard, please let me know. Put it in the comment section. Hereby sign off. Thank you. Thanks to watch my video.